It's actually a pretty nifty trick. So, let us say this is Vi, this is Vo, this is R1, this is R2, this is R3 and this is R4. What is the gain from the input to the output? Well, the voltage here is basically R2, R4 by R1, R3, correct? Now, what I am going to do, what did we discuss? So, what did we discuss just before this? What did we say? If the op amps are ideal and there is negative feedback around the op amps, evidently there is. So, what can you do? So, you can cut this off here, you can cut this off there and do what? Earlier, this node was connected to the output of, was being driven by the output of the first op amp. Now, all I am going to do is drive it with the output of the second op amp, and I am going to, this node, which was earlier being driven by the output of the second op amp, I am going to drive it with the first op amp. All right, and our claim is, what is the claim? What should happen or what should not happen? Nothing should change, right, as far as the node voltages are concerned, correct? Okay. So, in other words, this voltage must remain what it was and this voltage must remain what it was. Okay, is that true? How do you do this? Oh, well, first thing to do is redraw this confusing diagram into something less confusing. So, remember, see, look at this. This node is being driven by the output of this op amp. So, it looks like, I am just taking that op amp and drawing it this way, right, and R3 goes between the output of this, R3 goes between the output of the second op amp and the inverting terminal. So, this is R3, all right, and R4 goes between this is R4, and what happens? The output of the first op amp, and this is here. Does it make sense, people? Yeah. Now, you tell me what the output is. What is it? Yeah. So, well, this is Vi, this is virtual ground. So, what must this be? Minus R2 by R1 times Vi, and that must be equal to minus R2 by R1 times Vi must be equal to minus R3 by R4 times Vo, and therefore Vo must be R2 R4 by R1 R3 times Vi. Does that make sense, people? Right? So, if you have 3 op amps in a circuit, right, that basically means that you can generate multiple looking circuits. You know, I mean, they all look. I mean, this circuit, I don't know about you, but if I saw this for the first time, if I didn't show you this, if I didn't show you the one in the middle, right? I mean, the circuit on top looks. What comment can you make about the circuit on top and the circuit below? They look the same, or they look different, or you know, you don't care, or what? I mean, what is it? They look very, very different, right? But it turns out, amazingly, it turns out that you get the same transfer, not merely the same output, but also remember the junction here. Oops. The junction here, what is the voltage there? Minus R2 by R1. That corresponds to this junction here now, right? That's also minus R2 by R1 times. Yeah. Does it make sense? You might wonder, yeah, so what, right? Okay, all right, okay. I mean, I have to go to watch a movie in half an hour. I mean, how is this any more interesting than that? Okay, and of course, with ideal op amps, these two are exactly identical. Now, if the op amps become non-ideal, all right, then what comment can you make? Let's say the op amps don't have infinite bandwidth or infinite gain or whatever. What comment can we make about the behavior of these two circuits? I mean, generally the only thing you can expect is that they'll be different, correct? Because not after all the same network anymore, correct? Okay. Now, if you have multiple networks, I mean, in this case you have two networks which claim to do the same job when the op amp is ideal, right? When the op amp is not ideal, they will do the same job with different levels of effectiveness, correct? Because the op amp is not ideal. So, one circuit must be better than the other, right? I mean, you have two things, one must be greater or less than the other, okay? So, it might turn out that this circuit may be better than that circuit when the op amp is non-ideal, right? So, it turns out that in some applications, it turns out that a circuit derived by doing this, right, when the op amp is non-ideal, it actually turns out to be much better than the more straightforward looking circuit. Okay, we'll see that when we learn about filters a little down the road. Is this clear? Right? So that is one application of the M&A stamp of an ideal op amp. When you're doing this, I mean, you must be careful to ensure that there is DC, I mean, of course, the op amp is ideal and that there is DC negative feedback around the op amp, which is what is needed to ensure that the two input terminals of the op amp are a virtual short. Okay, otherwise it's it's not valid. And if you have 5 op amps in the circuit, ideal op amps in the circuit, then it's now a field day, right? You can now enumerate all possible circuits with and they'll all look very different, which means you can write 5 factorial papers, because nobody will be able to figure out that this circuit looks very different. I mean, they go, oh, wow, here is a new circuit, right? But actually it is the same thing drawn differently. You understand, right? Of course, before people discovered this, this actually happened because somebody, discovered, hey, here's a way of hooking up these two op amps to give you a, when the op amp is non-ideal, gives you, much better performance than, than the other one, than the more straightforward looking one, correct? And, then of course, after people started looking at it, then they figured out that, oops, these are all if the op amp is ideal, all these are nothing but the same circuit, right? But when the op amp is non-ideal, they all start behaving differently. So now it's like, treasure hunt, right? I mean, basically, if you have 4 op amps in your circuit, the guy who goes and quickly creates all the 4, all the million possible combinations and analyzes all of them, with the finite, op amp gain bandwidth, right? And you'll find, obviously, if you have, 10 people, it's always easy to find one which is better than the others, right? Or maybe, you find all of them are equally bad, and then you say, oh, you write a paper about that too, right? Okay, but this is a pretty. It certainly came across as quite surprising to me, right? I mean, if somebody showed me these 2 circuits and told me that these 2 are exactly identical, right? I wouldn't believe them, correct? But actually, when you write the M&A matrices for both these circuits, it is exactly the same M&A matrix. Does it make sense? Yes. Pardon? Actually, so that's a good point, right? So, again with network theory, right? I mean, they just assume that there is negative feedback around the op amp. It is the job of the circuit designer to go and make sure that there is indeed negative feedback. So as he points out, we just carried over the signs without bothering, right? Now, what should we do with the signs of this op amp? I mean, this op amp, of course, there is negative feedback around it. There is no issue. If you want negative feedback around this op amp, what should we do? You break the loop, okay, and then let's say you yank this voltage up. What happens to this voltage? This goes down, right? Or rather, this goes down. If this goes down, and let's say we assume the original signs like this, what happens if this goes down? This goes up. So is that negative feedback or positive feedback? Positive feedback. So what should we do? We go invert these signs. Okay. So whenever you do this, you have to make sure that there is negative feedback. Okay. So it's not necessary that the earlier signs that you used will work for the modified circuit, right? Of course, if you are a network theorist, then none of this stuff bothers you, because you just assume that some fellow's gone and done all that work, and then the op amp is an ideal element where V1 equal to V2, I1 equal to I2 equal to 0, and I3 can be arbitrary. This is question for the benefit of all of you. So he says, well, with an op amp, this confusion is probably arising because we have access to only one terminal, right? If we had access to both the terminals of the output port, would things have changed, right? If we had access to both terminals of the port, what would happen? You would get, you get another 1 and another -1 there, but it is still possible to associate. There are 2 ways of choosing +1 and -1, no? Right? So the problem is not solved. Okay? So it's got nothing to do with one port not being accessible, one terminal of the output port not being accessible. Okay? Is that clear? All right. So I think this is a good place to stop.